Hello everyone. So recitation number 7 was supposed to be on Turing machines, but since the exam got postponed, we actually had a revision recitation instead. I thought that might be more useful. So I'm going to go over the exercises that we did in class. I actually only had maybe 2 or 3 problems I wanted to solve, and I was hoping the rest of you would give me some problems that you tried to solve, but apparently nobody tried to solve anything. So with the rest of the session in class, we just solved some problems I had on backup. So anyway, we're going to go through these problems, but a lot of them, you'll notice that the ideas have been repeated, so you can always check previous recordings if you want more details on them. But anyway, starting with the pumping lemma, so just the regular pumping lemma, we have the description here, where we have some string s, we can break it down to x, y, z, and for any I, whether you're pumping up or pumping down, that XYZ should stay in the language no matter what the Y is, no matter what. Really, no matter how you break it down into XYZ. So I did solve this problem before, even in the recordings, but hey, let's do it once more. Why not? So we've seen these languages before. This one, we proved that it was not regular. This one was regular because we were able to make a DFA or an NFA for it. And finally, this one, we proved in a previous recording that it's not regular. But let's just go ahead and repeat the idea on how we did that. So step 1 was just, we wanted to see some of the strings that we had in there. So if k is 0, it's a power 0 power 3, which is just like a power 0. So it's like no a is the empty string. Then when k is 1, that's a power 3. So that's just 3 a's. And if we keep going, when it's 2, it's going to be 2 power 3, which is 8. Then after that, 3, which is going to be a power 27. When k is 4, that's going to give us a power 64, and so on. So this isn't a proof, but since we have these wide gaps between our elements, it's kind of an intuition that, hey, this probably might not be regular. So for example, if you have the string A28, A29, etc., all these languages, or all of these elements, they don't belong in our language. It has to be a power of 3. So the exponent has to be a power of 3. Okay. So what we're going to be doing is we're going to be kind of focusing on one string or one general string. And when we want to pump it, it has to be in this gap, right? Like for it to stay in the language, when you pump up, it has to reach the next element. But when we pump it up, or if we pump it down, we're going to make it so that it falls in that gap. But what is really it falling in the gap? Well, let's take a general element. So a general group of strings. So a power p power 3. The next element would be a power p plus 1 cubed. The previous element was a p minus 1 cubed. So this is what I'm trying to say. Like we have to talk it in general. I can't specifically for A27 do that. It has to be a general family of strings. Okay, so we pick this one. We say, hey, let s equal this string. When I pump it up, I'm gonna make it fall into this gap. Like it won't reach the next element. Now, in order for me to do that, what should I say? Well, when I pump it up, so I say s prime is x, y squared, z. It's all a's, right? And assume that y is some number of j's, a's. So this will be a p cubed plus j. So in order to prove it, like it's falling in this gap, 2 things. First, p cubed plus j has to be strictly bigger than p cubed. Like we're pumping up, so it's strictly bigger than this, but I also have to prove that it's strictly less than the next element, which is p plus 1 cubed. Now the first one should be pretty straightforward. This is true since j is the size of y, and y is what? Strictly positive. So no biggie here. The other one isn't hard, but it might not. But it might need a bit more details. So y is p plus j. Why does it fall short? Why isn't it able to reach p plus 1 cubed? Well, so question mark here. We want to prove this. And this and this. All right, so let's start with p plus 1, all of it cubed. We just want to do some expansion here. So this time I actually kind of memorized the formula. So we have p cubed here, then we have 1 cubed here, and it's 3p squared plus 3 1 squared times p, which is just going to be 3p. Okay, so this is the expansion. I can say that this is greater than or equal to p cubed plus 3p squared. And I'm going to replace this p with a j. Why? Since j is at most going to be p, right? J is the size of y at most it's going to be p if x was nothing. So by replacing p with j, this formula is true. It is greater than or equal to that. However, at some point I want to remove this greater than or the or equal part, because I want to prove that it's strictly bigger than p plus j. We could do that by removing this one, right? Like now I can say, oh, it's strictly bigger than p cubed plus 3p squared plus 3j. I can say that. So I got this strictly at some point, which is great. You do it in the middle, or if you do it at the end, it means, hey, at some point, hey, the original thing is going to be strictly bigger than whatever we reach at the end. Now, this part is greater than or equal. Let me write it here. What is it greater than or equal? What should I remove so it looks like what I want to prove? I want to reach p and j only. So, hey, I can say it's strictly bigger than... so p cubed, we can say it's bigger than p, right? We can remove the 3p squared, and instead of 3j, I could just say just j, all right? P cubed is definitely bigger than p. 3p squared, I just removed it, and 3j is definitely bigger than j. But in this part, I'm going to say greater than or equal because I can't be sure. Maybe I can be sure, but it's fine. Like I was able to get the strictly greater than because I removed the one. That's enough for me. So finally, I can say, so p plus 1 all of it cubed. It's definitely bigger than p plus j. So we're technically done. We were able to prove that p plus j is, let's call this finally instead of so. I was able to prove that p plus j is what? Strictly bigger than p cubed and strictly less than p plus 1 all of it cubed. I feel that I did a mistake somewhere. Let me double check because I think we should have here a p cubed. I might have messed up somewhere. So this should actually be a cubed. So where did I make my mistake? Yeah. My mistake was I didn't copy this correctly. This should have been p cubed plus j is less than this. So how can we fix that? I think simply we'll just leave this as p cubed. So remember when I said that p cubed is strictly bigger than p? While that is true if p is, of course, bigger than 1, I'll just leave it as it is. Hopefully that wasn't confusing. Okay, so I was able to prove this. That means p cubed plus j, like a power that, which is our s prime, does not belong to our language, so hey, the pumping lemma doesn't work. Remember that this is just a regular pumping lemma. It's not the advanced one. So usually with the pumping lemma, we make the example in a way where there's only like one case. This is technically one case, but we have to prove two things. Okay. Let's now do the next ones. But the point of this part was to show you that pumping lemma, what's the original idea? What are we trying to do? We pick some regular string, some random string, family of strings. We want to prove when we pump up or down, it doesn't stay in our language. This is exactly what we did here, but the idea was to know, oh, for it to not be in my language, it has to not be a power of something cubed. So it has to fall short when I'm pumping up. All right. Now let's do this one. So this is also another really cool idea for the pumping lemma, which confused a lot of people. So maybe we'll do another go at it now, and it'll be better. But let's read it. Prove that L, which is made up of the strings W, such that the number of zeros in W does not equal the number of ones in W. So W can be anything in your universe as long as it doesn't have an equal number of zeros and an equal number of ones. Okay. So the first way we did that, we tried to do something like we usually do before, right? Like I have to pick some random family of strings in my language. So we chose something like 0p, 1, 2p, right? This does belong in my language, which is important. The string that you pick has to be general, it has to be in your language. However, when we try to pump it up, right? If you try to pump this up, like, hey, s prime is x, y squared z, so 0p plus j, if y, the size of y is j, and it's definitely going to be some number of zeros, because it can't reach the ones, its xy has to be less than p. Okay, so if we do this, does this not belong in my language? This is true only if y, so if the size of y, which is j, is p. This will only be true in that case. So for a specific case, which isn't really what we want, right? You have to. This has to be true for whatever j is, for all the possibilities. If j is 1 or 2 or 3, all the way to p. So this string, this setup doesn't work. And really, if you try to do anything that we've usually been doing, it will not work either. Why? Because usually everything we've been doing so far, like say this, I have the language ANBN, right? And I choose the string APBP. And I say S prime is x, y squared, z. And I get some number of a's, right? This is everything we've been doing so far, and this will not belong to my language for any value of j, since j is strictly positive, right? For whatever value of j, this will always not belong to my language. Everything we've been doing so far was roughly some format of this, right? Like even the one we solved just now here. For whatever value of j, which is between these two, this will always be bigger than this, as less than this. So the pumping up doesn't reach it. This is what we've always been doing. But notice what we're doing. For whatever value of j, we're always using the same pumping, which is x squared, or which is y squared. We're always pumping up twice. So if j was just 1, we're getting AP plus 1 BP, which is again the squaring. If j is everything, we're getting a 2ppp, which is again, I'm pumping twice. And in both scenarios, it does not belong to the language. So what I'm trying to say here, it's not necessary that we always have the same pumping for whatever breakdown of the string. It just happened to be a coincidence so far that, oh, it works for whatever j is. It works for whatever j is. But as you'll see in this problem, it's going to be different. Depending on what j is, we're going to have different pumping. Let's read the formula or the description one more time of the formula. You have your string s. No matter how you break it down, the y and the x and the z, if you pump up or down, it has to stay in your language. That's all they're saying. There's nothing that's saying it has to be the same I for everything. All they're saying is no matter how you pump, it has to stay in the language. So if for each different for each different scenario, for each different y, if I'm able to find some I that doesn't work for it, then hey, that should be it. So back to this problem here. Let's try to do it not just for a specific j pumping, but for any number of pumps. And can we use that to figure out what our string could be? So I'll say 0p. It should be 0p, but what I'm trying to say is, what should I choose here as n? So what should n be in terms of p? Okay, so for temporary, we'll say, oh, this is my s. And when you pump, you're not going to pump just once. We're going to pump some number of times. We'll call that number m. Okay, and here we'll say 1 power n. This what do I get from this? I know that p plus j times m has to equal n. So if I take p to the other side, I'll get j times m is n minus p. So this tells me something about n minus p. It has to be a multiple of j, right? Like we're saying, oh, j times something is n minus p. So this could tell us something. Well, n minus p is going to be some multiple of j, but what is j? J is something between 0 and p. If I tell you, write me something that's a multiple of j, well, and j could be 1, or could be 2, or could be 3, all the way to p. So it could be p, or it could be p minus 1, p minus 2, etc. till you reach 1. Essentially, this is p factorial. So n, which remember, that's what we're trying to find, n should be, I'll take p back to the other side, so p factorial plus p. Think about that for a second. What did we do here? I started by saying, okay, my string will start with 0p, but what should n be so it works? Because that's the whole problem. When we try to specify n to be 2p, it didn't work because it would only work for a specific case. So I was trying to find n so that it would work for any case. But instead of specifying that I'll only pump up once j, I said I'll pump up m times, no matter what m is. I could be, if m was 2, you'd be getting what we were trying to do here with xy squared. Like or sorry, if m was 1, that means your y is squared, right? If m is 1, you're adding a j, that's what you get here. So when m is 1, you're getting xy squared, and so on. All right, so the relationship now tells me that p plus j times m should equal n. right? When these two are equal, that's when it no longer belongs to your language. Okay, if I take p to the other side, I get n minus p equals j times m. And that's when we said, oh, it has to be a multiple of it. So what is j? It's all of this. J could be anything between 0 and p. So if you multiply all the possibilities of j, you'll get that n minus p. It should be p factorial, and finally n should be this whole thing. So my string s should equal 0p, 1p factorial plus p. Like, now I know my string, now I can try to actually prove that it's not regular using the string. How would it have been different if... So why did it not work before? Because before, what we were saying is this. We were saying, oh, 0p plus j once and 1n. Like, I was essentially from this, all I really get is p plus j should equal n. And that's not really... There's no relationship between j and n in this scenario, other than maybe some linear formula, but that's not enough. Like, p plus j should equal n, right? Well, depending on what n is, j will be different. And we don't want that. We want for a specific n. So we'll choose a specific family of strings. So n has to be fixed. And for some fixing of n, it has to satisfy j for whatever it is. And that's what happened here. For whatever j is between these, n is a multiple of them. N is fixed, p factorial plus p, and for whatever j is, it's gonna work. Okay, so let's see that. So here, this is the second attempt. Now, if you didn't really understand, or if you're not convinced on how we got n should be this, or my string should be this, that's okay. Let's try to see maybe why it works. So assume that the question is telling you you're given the string s is 0p, 1p factorial plus p, and you just have to prove that, oh, using the string, it doesn't work. So I'll say s prime is what? So this is the question. What should I pump with? So let's take some cases and maybe we can figure out that. And remember, the string that we chose is what? Is 0p, 1p factorial, so p times p minus 1, and so on, times something. So I'll write here k as arbitrary, all the way to 1 plus p. What I'm trying to say is j, which is the size of your string, of y, has to be one of these. Like, say j is arbitrarily this. All you really have to do now when you pump up is pump up with the rest of j. So let's see it. If, for example, y was everything, so say y is 0p, right? How much should I pump? So x, y, y, z. What should the power here be so that I'm able to have equal number of zeros and ones? It should be everything except j. But I'm telling you j is p. So it's as if we're saying p minus 1 factorial. Why? Let's see what that means. So this part xy is 0p, and we have 0p. All of this is power p minus 1 factorial, and z is everything else, which is just going to be the 1. So this is, again, for a specific case, but what I'm trying to say, it's going to work for all the cases. So, but notice, p times p minus 1 factorial is going to get you what? P factorial. So for this specific case, it works. For the case where y is 0p, it works. I just have to pump up this much, p minus 1 factorial plus this one if you count. Okay, what about if y is just 1, 0? How much should I pump? Like I'm saying y or j is just this one. I'm only pumping once. So I have to pump up everything else, which is kind of like p factorial. So essentially here what we're saying is, where's the blue? Okay. So what I'm adding is, so say here we have a 0p, and I'm adding this y. It should be power p factorial. And then we have 1p factorial and a p. Right? Like this is the only part that I'm adding. This is the y power p factorial. Everything else should be the same. Should be my original string. Well, 1 times p factorial is 0p. It's p factorial and everything else. And this does not belong to my language, neither does this. Do you see what we did with these examples? I fixed some string s. Depending on the cases of what y could be, I'm able to find a pump that's ruining it and it's not making it my language. Again, before with here, we were always using the same pump. It was always plus j, like xy squared, and no matter what j is, it's working. The difference here is depending on what j is, depending on what y is, we're finding different pumps. So now we'll do it in general instead of a specific case. If y is some number of zeros, j, how much should I pump? So what should be here? Think about it. What did we do here? Oh, this was p much. So I was dividing p factorial over p. Like I'm removing the j part. I'm just pumping it with everything else. That's how we got the p minus 1 factorial. How do I get this p factorial? Well, it's p factorial divided by 1, which was the size of y. Just 1, 0. Same thing here. It's gonna be p factorial over j. Like you remove the j many to get everything else. That's the whole purpose of n being a multiple, n minus p being a multiple of j. Whoops, why did I write p? But if we do this, what will it look like in general? Well, we have some number of p's, or like 0p is the original. This is the only part that I'm adding, which is some number of j's which is y, right? All of this I'm saying it's power p factorial over p. This is how much I'm pumping. And this is a natural number. This pump is natural. Why? P factorial is a multiple of j. That's why it works. I'm able to always essentially cross this with this. So I'm left with p factorial. This is the whole point of making it a multiple of it. So that when you pump up like in general like this, you can remove the j and you're left with what you actually want. So this is 0p plus p factorial, 1p factorial plus p not belong to my language. And this is in general. So for whatever value of j, no matter how you break down the string, there will always be some pumping that doesn't work, which gives us the contradiction. Again, the original formula is saying, hey, no matter how you break it down, all the pumping should work. What we just proved is, hey, for no matter how you break it down, there is some pump that won't work which is the contradiction. We always have to prove that for all the cases, there is some pump that doesn't work. Again, before it just happened to be we're doing the same pumping every time. But in this scenario, no, it's depending on the case, we do a different pump. Which is really cool because this gives us like the true meaning of how this pumping lemma works. Hopefully you got that. And the reason I gave this example is so we could understand really how the pumping lemma works. So what I want from you is two things. Understand why what we usually do doesn't work. Maybe try to understand how we got the string, but most importantly, this part, which is why for every case we're having a different pumping. However, even though this idea is really cool, doesn't mean it's the best way to solve this. So for this question, we'll do second method. There's actually a much easier way to solve this, which is like this. Remember, I don't know if this is exactly closure properties, but it's along those lines. There's a formula, there's a rule that says, if the complement of a language is regular, that's equivalent to saying that the language itself is regular. Think about it. You just flip the accepting and non-accepting states. You flip them. So if you're able to prove that the complement of the language is regular, then the language itself is regular. This is similar to, so if I can prove that the complement of this language is not regular, that must mean that the original language is regular. But what is the complement of L here? Well, is the language W such that the number of zeros does equal the number of ones, right? This is the complement. So, and we can choose a much simpler string for this. Just choose, hey, 0p, 1p, just like AP, BP. We've seen this before. You can say, oh, xy squared z is s prime, 0p plus j. J is strictly positive, so definitely p plus j won't equal p, so they're no longer equal. So this does not belong to your language, L complement. Okay? Like we're doing the same thing, we've seen this many times, we're just proving the complement is not regular. So this is not regular, and we can conclude from that the language where the number of zeros in W does not equal the number of ones in W is also not regular. Because if it was, the complement should be, but we just proved that the complement is not. This is way faster, way easier to grasp than the other one, right? Like I would use this, if this came in the exam, I would use this method. Unless I was forced for some reason, like if the question said, oh, you must use the pumping lemma. Unless they say something like that, you should be free to do whatever you want. Okay. Moving forward. Give a regular expression that accepts a string of the following format. I'll just give you the answer. You can think about it yourself. So, what I would advise if you're trying to do a regular expression for something, think of general cases first before specific. Like, oh, there is a specific case that's in this case. So if you remember this question, we made a DFA for it in the first recitation, and I actually told you to do a regex for it. In case you didn't. So one way of trying to solve this is, oh, the general case, I must have some odd A, right? Which is just A star. I must have also odd B or even B. So this is, I'll say, oh, A star A, union BB star. Like I'm thinking of specific cases and my solution might get very long. So this is thinking specific. Instead, let's think general first, and then we'll think specific. So thinking general cases. which is the alternating. How can I get the alternating feeling? So let's say I want odd A followed by even B. And this, I want it to happen as much as I want, right? This is me trying to think of a general case, but there's a problem with it. If I leave it like this, I can choose A and choose nothing here because they're stars. Then when I loop back, I can choose A again, and I get even A's. So this is a problem. Instead, what I do is the following. I could say, hey, make both of them star. That could work. I could say this should be strictly and this should be strictly. Now this works. Like I'm gonna get now the format, oh, odd, even, odd, even, odd, even. But the problem is what? The even part, no problem. BB is even. But with A, I'm forcing it to always be of length, at least 3. Right? But if it was just a single length, like just one A, that's also odd. So this should actually be a star. Why? I can now have any length odd A. It could be 1, could be 3, could be 5. Plus, the format is odd, even, odd, even, odd, even. Think about it. If I choose a single A, I'm forced to have it followed by at least some even number of P's, right? So I can't have, so when I loop back, when I choose A again, there's going to be some even B in between. Could be 2, 4, whatever. Okay, great. So I'm not forcing a specific constraint that I don't want, like it having at least length 3. I don't want that. And then the format is good. Now, so we thought general. Now we can think more specific. Like I'm forcing it to always start with A, right? Like if you think about it, or actually I'm not forcing it to start with A. It could start with B, right? It could actually start with B. Oh no, my bad. I am forcing it to start with A because I have here a specific A. So I'm always forcing it to start with A. So I have to give it the option. It could start with B. Do that by saying here B, B, star. I'm giving the option you could start with B if you want. Same thing at the end. I'm forcing it to now end with B. I'll give it the option to end with A. But I can't write it like this because that would make it, again, same problem. I could choose 2 A's that way. And I don't want to do this either because even that might not work. I want to give it the option to end with A, and I'll do that by saying this. AA star, and all of this question mark. The option, remember the question mark, so if I say A question mark, just means either A or nothing. So when I say this whole thing, which is odd A question mark, it means either I end with odd A or I end with nothing. And this should be this should generate everything. Do we generate just B's alone? Yes. Take this to be nothing and this to be nothing. I'm getting BB star. Do I generate B's alone, or sorry, A's alone? Yes. Take this nothing, and you get here odd A. Do I get the general format? Yes, I do. I can get odd, even, as much as I want. Okay, so this is how we do this old trend. Okay. Moving forward. By the way, during the session at this point, like every time I finish something, I was always asking like, hey, do you have any questions on regular expressions? Do you have any questions on pumping lemma? And so on. For CFGs, I'm not gonna solve this one because I already told you the idea on how to solve it in an older recording. So you can just go back to that and see how you could solve this one. The idea was something similar to how many states I have. Like try to make your variables mean something. Like for example, SEE could be even ones, even zeros. SEO, even zeros, odd ones. SOE, odd zeros, even ones. Odd 0 0 like O, like odd, okay, and so on. Like this would be your starting variable. And if you read a 0, you'd go to SOE, which is this one. Like, oh, now I have an odd number of zeros and an even number of ones, and so on. If I read a 1, that means my number of ones became odd, so I'll go to this one. Or I can end here. Like this will be the only variable that has the option to end, because this is where you want to end, when you have an even number of zeros and an even number of ones. So you'll only write epsilon here. Everything else will just have transitions. This is similar like when if you want to do a DFA for this, you're only going to have one accept state, right? The other ones won't be accepting. The only one will be accepting the even. Same thing here. The only one that's going to end or have the option to stop is the even. Okay. PDA. So let's do part C. We did this one before. This one isn't hard. You can think about it yourself. Let's do this one because we didn't solve enough, or we didn't create enough PDAs in my opinion. Okay. The number of A's in W should equal the number of B's in W. Before you dive into write and trying to draw something, think of what it could be like, right? Like do some cases. Like say you have the string A, B, 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 and A. This should be accepted in your language. But how would you handle it? So I start parsing from the very beginning. So say this is your stack. Just think about it. What will you do during the parsing of the string? Of course, step 1 is pushing $1, so you can know when it's empty. So you read an A. What are you gonna do? There's nothing really you can do but push an A. Because once you keep reading, you're gonna lose that A. Right now your stack is empty, so all you could really do is push that A. Then you read another A. Push that too. You start reading your B's. So if I read one B, well, what should I do? I'll pop that A. If I read another B, I'll pop that A too. When I get to the third B, what should I do? My stack is empty and I'm reading a B. Well, push that B. Otherwise, you're going to lose information. I can't push an A, it's a B. So I push a B, and then when I read the A, I'll pop that B. Do you see what I'm saying? The stack is always keeping track of what the surplus you have so far. Like when I first read the 2 A's, this means, and my stack had 2 A's, this means so far I have 2 more A's than I have B's. Then when I was here, and I only had the B, I have 1 more B than I have A's so far. You will only accept when you have equal numbers. What does it mean to have equal numbers? Oh, like they're both the same. Okay. So what are the cases here? We can break them down into 2 big cases. When you read A, what's happening? If I read the A, so let's now just focus on reading the A. What are the possibilities? Your stack could be empty. If that's the case, push an A. Or your stack could already have an A in it. Right? Like it's not empty, it already has an A. What do? Push an A too. Finally, what if your stack had some number of B's in it? Well, you'll pop the B. Is there really any other case? If you read an A, either the stack is empty, or it already has A's, or it already has B's. It has to be one of these three cases. And same thing if we were doing it for the B's, right? Same scenario. When I read the B, what are the possibilities? Stack is empty. Push a B. Stack already has a B, so I'll push a B. Or if it already had an A, I'll pop that A. So if these are all my cases, or this is the functionality of my PDA, how can I actually write it? So you have to go through, so like essentially every one of these points are like a transition. Like depending on this, you'll do this. So you just have to make them into a PDA. Try to do that here. Okay, so starting with the 1. Step 1 is always push $1. So if I read nothing, pop nothing, I'll just push $1. Then we have, then if at some point, say you read the $sign, I wrote that wrong, but I go to the accept state. So it's actually read nothing and pop the $. What I'm trying to imply is yes, essentially everything we have written up there is gonna need only one state. So read nothing, pop the $. Why? I'm gonna just loop here. So let's focus on the blue part, yes? If I read an A and there's $, I should push an A. But what does it mean? What does it mean that I have $? So I'm reading an A. The stack has $. Like if this is reading the top of your stack, but it's not only reading the top of your stack, it's also popping it. So what I should push back is $A. Now this is wrong syntax. We'll fix that in a moment. But try to understand the idea. Like you can't push more than one symbol. So it's read A, pop $. But imagine I'm able to push $, then A right on top of that. That's what I want, right? We'll fix it in a second, but does it make sense? I read an A. I'm popping the $, which means, oh, my stack is empty. So I have to push an A. But I can't just push an A, that would be wrong. I have to push back the $, that I popped, so I can know that the stack is empty at some point in the future. Keep going. What if I already have an A? So I'm reading an A. I'm popping an A. This popping of the A tells me, oh, I have A's. So I have to push the new A, and I have to push the old A that I popped. Same thing that we just said with the $sign. But now for it's like the A you have to push back instead of the $. And finally, when you pop the B, or if you read a B and there's an A, you pop it, then you do nothing. That's it. That's it. It's going to be the same thing for B, but with proper syntax. So let's do B actually with proper syntax. I'll write first the easiest part of the B, which is the last one. If you read an A and there's a B, you pop it. Let's proper, so these two are wrong syntax. Think about it. How I want to do the same thing, but how can I do it in proper syntax this time? So let's do the first one with a $sign. I read a B. Oh, my stack is empty. Push back that $sign that you popped. go to some temporary state, then go back and push the B that you read. Don't pop anything. But what should you read? Nothing. It's a free transition, right? I read a B, pop the dollar, push back that dollar. So this just pushes back the dollar that I read, but lets me know that I should push a B because my stack was empty. So when I go back with the dollar, I just push the B. And actually, I could also put here another transition. I could put, if I read a B, and there's a B, push that B. Does it make sense? This is the case where you already had B's. So first you're reading a B, you're popping the B, which tells you, oh, you have more B's. So you push back the B that you read, and then when you come back, you push the new B. In both cases, when you go back, you have to push a B. It's just a matter of first you have to push back what you popped. This is the proper way of doing it. I'll do the same thing now here for the A. If I read an A, pop an A, push an A, or if I read an A and I pop the dollar, I push the dollar. And when I come back, I have to push that new A. Read nothing, pop nothing, push an A. And now, like, I can remove this wrong syntax. Let's actually leave it readable. Just make a sign that it's the way that it's written is wrong. Okay. So the logic is correct, but the way it was written is not correct. All right. And here, the proper way of writing it. Hopefully this made sense. A lot of arrows floating around. Oh yeah. Let's do one more PDA. So what is this language? As always, like, you can always pause and try to think of the problem yourself. So L, some number of A's, followed by W, followed by CK. However, the K is how many A's you have in W. So for example, I could read some 3 A's. Then I start reading my W, BA, and then C could be 2 C's, right? So these 2 C's are these 2 A's. Well, just do it. So I know I just said before, try to think of the flow before, which is correct. The flow here seems pretty straightforward. Like, try to literally just translate what's happening. What's the first thing I'm doing? I'm reading some A's. I'm not pushing those A's. I'll only push the A's of the W. So just read some A's, pop nothing, push nothing. Then I go with a free transition to the other side. So this is read A. And here I'm going to read W. Okay. What do I do when I read W? If I read an A, I should push it. If I read a B, well, I just read it. I don't have to do anything. Retransition to the third area, read C. Right, like my string or my PDA is 3 parts: reading A star, reading W, reading CK, like it's right there. So finally, when you read C, you'll pop the A's and you'll push nothing. When you read the $sign again, or sorry, when your stack is empty, so you pop the $sign, that's when you accept. Does it make sense? I'm reading A's, reading W, reading C's. However, so this works for this one. Because, oh, when I read the B, that's when my W started. But even if you had a string like this, and say I have 3 C's, this is also gonna work. Like your W is here. This is also gonna work. Why? Remember, PDAs are non-deterministic. So it's gonna try all the possibilities. Like in the first run, so imagine here you have your tree. In the first attempt, it'll read 5 A's. Like it'll read the whole 5 A's and push them all in the stack. 1, 2, 3, 4, 5. It's gonna push all the A's at the beginning. Then it's gonna read BA. So the rest of it is gonna read BA as your W. And then it'll start reading C's. That's not gonna work because you have 5 A's and you're gonna read 3 C's. It's not gonna work. That's one attempt. Then in another attempt, it's only gonna read 4 A's. That also won't work because you're pushing 4 A's. Oh, sorry, my bad. My bad. It's actually when you read the 5 A's, you only push 1 A, right? Like when you read the first 5 A's randomly here, you're only pushing the A here. You're not pushing these two as well. When you read the 4 A's, you only push 2 A's now. This A and this A. And finally, there's going to be an attempt where you only read 3 A's at the beginning, like you're burning those 3 A's. And you push the A's of the W, which work. And since PDAs are non-deterministic, it only matters if one formula works, or if one route works. That's all you care about. So here I was focusing on this part, the reading of the A's happening first. It could have happened in another way, right? Like there might have been a route where, oh, you in the reading of the W, you assume everything is W. So you push everything. There's lots of ways it could go wrong, but there will be a route where it works, and that's what you care about. That route will be accepted. Okay. So I'm gonna do these two because we have a recording that's doing GNFAs and we have a recording that's doing Chomsky. You can revise those in case. So we did do a part of these in class. We did all the Chomsky and we did a part of this. Just revise the lectures. Like here, remember the important thing when you want to remove something is you add a new start state. You add a new accepting state. And for the accepting, so the start state goes to the old start. And no matter how many accepting states you have, you must add an epsilon to your new accepting. Like if Q4 was accepting, you'd also make it go to the new accepting. And then you start removing. Like if you want to remove 1, you'll check all the cases, all the routes that pass through 1. Like 0 goes to 1, goes to 2. 2 goes to 1, goes back to 2. 4 goes to 1, goes back to 2. If this is the first time you're seeing this, go back and revise the lecture on GNFAs where I explained that in detail. Okay. Also go back. It's in the same lecture, in the same recording. I also go on Chomsky. Okay, but really important, try to go over the suggested problems, right? Like, there are some really cool ideas here that we didn't pass in class, and there's roughly a solution of them too. So in this one, trying to remember what this symbol means, but essentially these are your transitions. So here they're telling you, oh, do all the transitions, all the possibilities for when you start at the start state 1 and you're reading AB, or when you're reading this. Since it's NFA, there are a lot of possibilities. Like there was epsilon. Was there an epsilon here? Maybe not epsilon, but there are different transitions. Like 1 on A goes to 1 and 2, and 1 on B goes to 1. Where are you? Okay, so I think it was this one. So it shows you all the different routes. So this by the way, why it tells you it's an NFA. Like it's saying when you're at state 1 and you read A, you can go to 1 or you can go to state 2. Like there are two different A's coming out. So here, when you're at 1 and you read an A, you can either go to 1, like stay where you are, or you can go to 2. So there are two possibilities. You might end up at 1 or you might end up at 3. And here's another one. When you're reading A, B, A, A, B. So really cool stuff. Like this, we've never done this in class. Like maybe right now I gave an abstraction idea of it, where I'm reading 5 A's, 4 A's, or 3 A's. This is maybe more practical. There's also another cool problem I remember, which is, yeah, this one. For a language L over 0, 1, denote L cut to be U. AU belongs to L for some A in your alphabet. Not the letter A like some arbitrary. Like A could be either 0 or 1. So it's the set, this means it's the set of strings in L cutting off the first character. So if 0, 1, 0 was an L, 1, 0 would be an L cut. Again, you're given a language L and a language L cut. L cut is simply L, but without the first character. So if this was L, what will L cut be? Yeah, right? It's read only for some reason. But if this was L, what will L cut be? Well, you cut the first character here, so you're left with epsilon. You cut the first character, so you remove this, this, and this. You're just removing the first character. This will be L. So, browsing through suggested problems. This is exercise 16. And here 0n 1n, so essentially this will just be 0n minus 1 1n. However, n will change, right? And now instead of n being 0 1 2, n will start from 1 because you can have a negative. So you're cutting the first 0 from here. So it's 0 n minus 1 1n, and n has to be greater than or equal to 1. Show that if L is regular, then L cut is regular. So this is really cool. This is going back to the abstraction part from the first recitation. If you're given L is regular, how can you prove that L cut is regular? So I'm given L is regular. So there is some machine M1 that accepts the language L. It has some, so it has, assume it's a DFA, right? So it has someone here, some 0 here, and then you have a whole bunch of states and some accepting states too. How can I make some M cut that accepts, or n2 that accepts L cut. How could I do that? Well, it feels like I should literally cut this first part, right? Like I'll make, doesn't have to be a DFA, it could be an NFA. I'll make a new start state that goes on epsilon to these old states. So I'll call this, for example, Q1, Q2, Q1, Q2. Instead of going on 1 and 0 here, we'll make it go on epsilon. So like it's a free transition. You're literally cutting those transitions out. And like even if for some reason, no, okay, I think this is good enough. I'm thinking of some scenario where I go back here on some state. Like, would that be a problem? Going back here, it could cause some problems. But this is a start, like removing the parse. Let's actually check the solution. So I'd always advise don't check the solution right away. Like here, okay, here I could check the solution because we've made some good progress. Like I could argue, I could even start think a bit more, like maybe 5 or 10 minutes before I check the solution for this problem. If I'm not short on time. So I go now with a solution, it's 16. Let's see what they say. L is regular, then there is a DFA for it that accepts A. We want to show that L is regular, so we'll consider consecutive NFA and L cut. For every state reachable by one transition from the start, we add an epsilon transition Q0. Oh, okay, this is actually really cool. So do you understand what they said here? This is very similar to what I did, but much better. For every state that is reachable by one transition from the start, we add an epsilon transition, Q0. So for example, in this scenario, the reachable states on one transition from my start, so this is S my start, or Q0, are Q1 and Q2. Q1 and Q2 are the only states that I can reach them with one transition. So they're saying add the epsilon transition as I did. However, they're not saying remove the old transitions. They're just saying add one. Like 1 and 0 will still be there. I'm not removing 1 and 0. I'm just adding the epsilon, and that will give me the option to go like at the beginning on a free. So I'm like cutting it. Because as I mentioned before, there's the problem if what if I go back at some point? If I go back and then I have to read a 1, that's different than if I go back and I just get a free transition right away. Like I want to only cut it once at the beginning. I don't want to cut it multiple times. So adding epsilon instead of replacing epsilon with whatever you had before, that's really cool. Does that make sense? For every state reachable by one transition from the start, we add an epsilon. We don't remove the old transitions, we only add an epsilon. I think that should be fine. Now you might argue, hey, if I'm adding epsilon, I could still use 1 to go. Doesn't that mean my language will be the same as before? Like if I'm simply adding epsilon, doesn't that mean my language will still create everything that I created before, but more? Like it's kind of weird, right? Like we're saying L cut is removing an element from L, but technically it could have more items. Yeah, maybe. Why not? Like if we're talking general, why not? So here we said n minus 1, and n could be 1, 2, 3, right? This is for L cut when we cut. Does this get me more items than the one before? So if n is 1, I'm able to get 1 on its own. N is 2. So that's interesting. Am I able to still create everything that I was able to create before? Doesn't seem like it with this example. Because this example, what does it create? From this, I'm able to get 1 on its own, or I can get 0, 1, 1, 0, 0, 1, 1, 1. Like I always have 1 more, but it doesn't feel like I could create 0 and 1 and. But with here, if I do this idea, I feel like I can get 0 and 1 and. So that's something we'd have to think about. Okay, so the solution actually might be missing something. Okay, so I think the proper solution, so go with me a bit. Like this is what studying is, right? Like we have to think about things. We don't have to get the answer right away. What I think we should do, like to get the ultimate solution, like this is a pretty good solution, but maybe to get the ultimate solution, what we could do is the following. I'll draw it here. I'll still make epsilon go here, epsilon go here. So my start, Q0 and Q1, or this was Q2 and this was Q1. I'll still do this. So I'm replacing epsilon instead of 1, 0. Like all the reachable state by one transition, I'm replacing them with epsilon. And not only that, any state, so any old transition that would have went to my start, I'll make them go to a new temporary state. And this temporary state will have the transitions that go back. So let me explain that better. First of all, I'll create a temporary state that can also go to Q1 and to Q2 depending on what the transitions were. Like I'm going with what I wrote here, 1, 0. I'll make a new state that can go there. And if some state used to before go back to the start, I'll make it no, go back to that temporary instead. Does that make sense? I imagine you literally copied pasted the first start state somewhere, which is literally like I copied pasted it. It goes to the same places that the old state used to go to. And if any transition used to go to the start, now it goes to this like temporary start. And my start now, all it does, it kickstarts my solution. So I think this is what we should do. Like to make this better, it's going to be wordy, but it's like everything I said. So for every state reachable from transition from our side, we add Q0. Like, and it's going to be really wordy. So step 1 would be make a copy of the start state that has the same transitions going into and out of it. So exactly the same start state, it's the same, but it's just a random state. Make the start state have these transitions. Epsilon transition to any state reachable by one transition. So the start state should have an epsilon transition to any state that it can reach with one transition. And finally, remove any transition, any old in-out transition from the start state. Does that make sense? Step 1, I made a copy of my old state, of my old start state, which is this one. It has everything before. It can go 1, 0 to the... It has everything outgoing and everything ingoing to it. My start state, I add the epsilons. And any old transition that was coming in or coming out from my start, I cancel all of them. I cancel these. And that way I ensure the cutting of it. I think this is the best way to put it. Yeah. So usually the solutions assume they're more like guidelines. Like they give you the idea, but they might not always take you all the way through. And this is like what I usually do. Like in case you ever, like when I was solving maybe this one, you were thinking, oh, how should I be able to right away figure out a solution for this? Or when I was solving this one, oh, how should I think of p factorial p? How should I think of this scenario? You don't right away think about it. Like, look how much time it took me to actually maybe get the proper solution for this one, right? How much have I been going on and on right now? It takes time to properly think of a solution for something, then you have to solve it again and again so it becomes really refined, and then you can, then maybe you could solve this problem right away. If you've solved it already like 4 or 5 times before, you can solve it right away. Okay, so just try to get as much practice as you can. I actually wanted to solve a few more problems, but this one took a lot of time. So just go over the problem, see what you like, see what stands out. Like I would, personally, I like abstraction problems, but just see whatever problem you're maybe weak, you feel you're weak at. Like, oh, this is pretty cool. You can try to solve this one. In an attempt to show that EP, which is the language of even length palindrome, is not regular using the pumping lemma, they propose the following. They're asking you what is wrong with this algorithm or with this attempt. So you can pause and think for a second. Okay, so assume that EP is regular. Let P be the pumping length. Da-da-da. What is the problem? The problem is with S. EP is language of even palindromes. This S is odd. It's 0p, 1, 0p. It's odd. Had it been 0p, 1, 1, 0p, it would have been even, it would have been fine. So this, we mentioned this a lot. Make sure the string you choose is general family of strings and it actually belongs to your language. If right away you pick a string that doesn't belong in your language, when you pop up or down, it doesn't matter if it's in or not. So make the correction, then complete. So now you have 0p, 1, 1, 0p. Now you just have to prove why it's not regular. And so on. True or false. Of course, solve all of these. We solved a few of them in class, like we solved this one, x, y, x reverse. Like some of the problems I usually solve, I get them from the suggested problems to help you kickstart solving them yourself. This is the second for chapter 2. See what you can do here. Like, this is interesting, trying to understand what's happening here. And oh, this is actually really cool. So consider this language. A 0n hashtag w 0n. Okay, so this is obviously depending on w. Okay. Okay, so this is not going to be regular because you have 0n and 1n and you have something in the middle. List the first 6 strings of A in lexicographic order, which what they mean is imagine alphabetical order. Or like something like that. Like this, first you list the strings of length 1, then length 2, then length 3, but you only want 6 of them. But yeah, like let's actually check the solution, see what they did there. So this is 19 in chapter 2. Okay, it's right here. So it's hashtag alone. So length 1 is only hashtag. That's when probably yeah, when W is nothing and N is 0. Then we have hashtag 0, hashtag 1. That's when W is something. So they wrote the W strings essentially. All right. Using the pumping lemma, this is actually what we already know. Like with part A, this is usually what we do in general. Like with today, going back to this problem, this first pumping lemma. Where are you? This one. What did I do before even starting to solve it? I wrote some things for the language. Epsilon, 3As, 8As, to kind of get an idea of what this language is. That's not a bad idea in general to do. Use the pumping lemma to show that it's not regular. Show that it's context-free by giving a CFG for it. That's not bad. That's a cool idea. And so on. Then finally, the PDA, they tell you to fill on those maths. So you can check that out. And of course, we probably have some true or false at the beginning, at the end. I'm not gonna say more than this. That's just keep solving and solving. Okay. And I'll see you in the next one. Goodbye.